We will now improve our approximation for the instantaneous rate of change. In the last video, we calculated approximations for the instantaneous velocity for each time t. The reason these were approximations was because we had to use a time interval to approximate the velocity at a particular time. To better approximate the rate of change at a point, we can make the interval containing the point smaller. But to do this, we have to have more data points. Let's revisit approximating the instantaneous velocity at t equals 0 with the knowledge that after half a second, our object is 37.5 feet in the air. Approximating the instantaneous velocity here, we get that v of 0 is our change in position, 37.5 minus 4, over our change in time, which is now only half a second. Calculating this, we get 33.5 over 0.5, which is 67. It's worth noting that the interval from t equals 0 to t equals a half is a better approximation to the point t equals 0 than the interval t equals 0 to t equals 1, since it is smaller and a smaller interval better represents a single point. So our approximation that v of 0 is roughly 67 is a more accurate approximation than our earlier approximation of v of 0 is roughly 59. So how do we make an even better approximation? Pick an even closer point. Now let's say that we know our height at 0.1 second is 11.34. Approximating v of 0, we get that our change in position is 11.34 minus 4, which is 7.34, over our change in time, which here is only 0.1. Computing this, we get that the velocity at 0 is roughly 73.4. Again, the interval t equals 0 to t equals 0.1 is a better approximation to the point t equals 0 than the interval from 0 to 5, since it is smaller and again better represents a single point. So our new approximation v of 0 is roughly 73.4 is a more accurate approximation than our earlier approximation of v of 0 is roughly 67. So how do we make an even better approximation? We have to pick an even closer point. Let's now approximate the instantaneous velocity at t equals 0 with the knowledge that the height at 0.01 second is 4.7484. Again, we calculate v of 0 as our change in position, 4.7484 minus 4, which is 0.7484, over our change in time, which is now 0.01. Calculating this, we get that v of 0 is roughly 74.84. Because it's smaller than our last interval from 0 to 0.1, so again it better represents a single point. So our conclusion is that v of 0, roughly being 74.84, is a more accurate approximation than our last approximation of v of 0 being roughly 73.4. So how do we make it even better than that? We have to pick an even closer point. Now let's approximate the instantaneous velocity at t equals 0 using the interval from 0 to 0.001 second. Here, doing the same calculation, we get that v of 0 is roughly 74.984. And again, we have a better interval than we did before, because the interval from 0 to 0.001 better represents a single point than the interval from 0 to 0.01. So our new approximation, v of 0 is roughly 79.984, is a more accurate approximation than our earlier one of v of 0 is roughly 74.84. And how do we make an even better approximation? We have to pick an even closer point. Let's again approximate the instantaneous velocity at t equals 0 using the interval from 0 to 0.0001. Here in computing our approximation for v of 0, we get 74.9984. Again, this smaller interval is a better representative of a point than our previous interval. So we get a better approximation for v of 0 than we had before. So how do we make an even better approximation? We have to pick an even closer point. But when do we stop? We can always find a closer point. So when is the point close enough? Let's be more methodical about what we're doing. Define delta t as the change in t. So we've been approximating v of 0 as our change in position over change in time. To find change in position, we need to know our position at 0 plus delta t, our ending position, minus the position at s of 0, our starting position, and take their difference. What we've found so far is that when delta t equals 1, our approximation is that v of 0 is 59. If we shrink delta t to 0.5, our approximation becomes 67. When delta t is 0.1, our approximation is 73.4. When delta t is 0.01, our approximation is 74.84. We calculated down to delta t equals 0.0001 to find that our approximation of v of 0 is 74.9984. And if we were to calculate this for delta t equals 0.00001, we'd find that the approximation for v of 0 is 74.99984. So where does it look like these approximations are heading? It seems that as delta t gets smaller and goes all the way down to 0, that we'll get v of 0 equals 75. Note that we're implying this is no longer an approximation. We formally say this as v of 0 equals the limit as delta t goes to 0 of what we were just calculating. S of 0 plus delta t minus s of 0, which is our change in s, over the change in t, delta t. And in general, if we want to do this at t equals a, the velocity at time a is the limit as delta t goes to 0 of s of a plus delta t minus s of a all over delta t. Notice these two equations are the same with a in place of 0.